Yeah, good morning again. So today, as Murat already introduced, my talk will be about age-eU associations in thermochronology. In this case, especially spurious age-eU associations, but I will explain that in a minute. And in contrast to yesterday, this will not be about a specific method, but in more general terms, looking across different thermochronological methods. So let's just start here. First of all, I want to introduce you to the occurrence of age-eU associations. So EU, as I already showed you yesterday, is like the effective uranium or uranium and thorium concentrations recalculated to the decay rate of uranium. And it is often used in thermochronology as an index for monitoring the data. And what we can see here on this slide are three diagrams, typical scatter diagrams of age, of thermochronological age against EU for three different methods: the apatite fission track, zircon, uranium, thorium, helium, and zircon, Raman. And what we can see in all of those three plots is that we have a negative association between the age and the effective uranium content. Or we can say, usually the ages become younger within the sample with increasing content of uranium and thorium. And this is actually a really interesting phenomenon that we find in different thermochronological methods. And so the big question arises, why does this happen? So the standard interpretation for that, and I think it's a pretty good idea, is the age reset interpretation. So this interpretation basically says that EU is a measure of alpha radiation damage, which is pretty logical, as alpha radiation damage, as I told you yesterday, accumulates through the decay of uranium and thorium, right? And so if we have one sample with many different grains in there, usually the ones that are most damaged, the most damaged zircon, for example, in a sample, should be the one that has the highest uranium and thorium or effective uranium content. And now the idea behind this is that as the radiation damage destroys the structure of a mineral, of a zircon or a titanite or an apatite, the retentivity for the daughter product of the dating method changes with radiation damage and is therefore dependent on the effective uranium. So this is, for example, shown here on the right. I just put in two figures to not overwhelm you here. There's the upper one, which is a nice experimental data from Günther and others. And here they plotted the closure temperature of the zircon helium system against the alpha dose, so the amount of alpha events that have taken place. We saw that yesterday. So, and what we can see here is that we actually have a trend of closure temperature slightly increasing at low alpha doses. And then we have more or less a threshold dose above which the closure temperature strongly decreases with increasing damage. So it is interpreted that at low levels of radiation damage, the closure temperature only changes a little with increasing damage, but above a certain threshold, the crystal lattice breaks down and it becomes very, very easy for the helium to escape, and therefore the zircon becomes very sensitive to a thermal reset. A pretty similar observation was made by Danishik and others, and you can see it down here. So they actually mapped zircon grains and looked at the effective uranium also and the distribution of helium within those grains. And what we can see here, like I want only to focus your attention on this zone in the right map, where it's like which has like this yellow reddish color, which indicates like very, very high amounts of effective uranium. So we are in the thousands ppms. And actually in this zone where we have very high effective uranium and probably the highest radiation damage within that grain, it was not possible to find any helium. So the helium in there was, the content was very little. And also we can interpret this in terms of the strong radiation damage within the grain, making the helium escape from the grain. So this is like the main interpretation of this phenomenon, and it actually has been put forward for many different dating systems. So basically apatite and zircon fission track, and apatite zircon titanium titanite helium, and also for the Raman dating I talked about yesterday. So for most of these methods, this relationship between age and effective uranium looks the same as I showed you on the previous slide. The apatite helium is a bit special. Here, actually, the relationship between age and effective uranium is usually a positive association. But anyway, what you need to remember is that for all these methods, such an association has been observed. And for all of these systems, it's usually interpreted in terms of radiation damage. So if we have a data set, what does this mean? Like in the usual case of a negative association, it means that basically the age of a low effective uranium grain, so the one that says here unreset age, is assumed to have seen or to be very, very resistant to loss of daughters, so to helium loss or to fission track annealing, for example. Whereas the higher the EU gets, the more susceptible to fission track annealing or helium loss a grain should become. So here we have like a damage enhanced age reset. So if we take such a sample, the ones on the right are the ones that will suffer most from the thermal event, whereas the ones to the left are more stable. Okay. So now we can ask the question, well, it's a very plausible explanation, I would say, but can we make a straightforward deduction from an age-eU association that we observe in our data to a radiation damage enhanced annealing in our sample? So just the question, is it always the case that radiation damage brings us this pattern? And if we see it in our sample, can we then use this? And to test it, we set out with my co-authors to find out. And what we basically did was look at age-eU correlated data sets. And here we took apatite from Duluth FC1 and plotted the age against the uranium. So here we saw, okay, we have like a scattered, but anyway, it's there. We have a negative age-eU correlation. And now the question was, how do we test if there is enhanced annealing or radiation damage? No, age reset, fission track annealing related to radiation damage. And of course, if we wanted to monitor fission track annealing, we used the fission track length. So we measured lots of fission track lengths within these FC1 grains, and we also plotted it against uranium. So usually, if for this sample, the radiation damage enhanced annealing hypothesis is true, we would obviously expect that the grains that have most uranium and most radiation damage should have also shorter tracks than the ones that have lower uranium. But looking at the second plot here of the length against the uranium, we see there is no relationship at all. So like the ones with the least uranium and the ones with the highest uranium, none of them has been annealed more than the other, right? And so we can say that the age difference that we see between the low uranium and the high uranium grains is not due to preferred annealing of the high uranium grains. We did the same then for the zircon-Raman system. So we took a sample here, which is called DX46, and we also got a nice age-eU correlation for that sample. Again, a negative correlation looks very much like the one we saw on the previous slide. And what we did then was to use our annealing detection ratio, so the one that I showed you yesterday, just to remember quickly again. So the different Raman bands that we have have a different sensitivity to thermal annealing, and that is why we can actually use damage estimates from different Raman bands to detect if a sample has been annealed or not. And in this case, we usually use the so-called D2-DER ratio, which is 1 for an unannealed zircon, and which rises up to values of about 2 during thermal annealing of zircon. And again, we plotted this annealing ratio against our effective uranium. And what we found was that even though those different zircon grains give us very different thermochronometric age, they all have the same annealing ratio, and they're all basically completely unannealed. So again, we can say the age difference that we see between low damage or low effective uranium grains and higher damage or higher effective uranium grains is not due to thermal annealing or to radiation damage enhanced annealing. So actually, we cannot make a straightforward deduction of radiation damage enhanced annealing from an age-eU association, because age-eU association can exist without any radiation damage enhanced annealing. That begs the question, how do we explain the age-eU associations that we see then if it's not by radiation damage? And here I just want to take you back a step and see what do all of these different methods where this phenomenon happens have in common. And of course, we're in radiometric dating, so all of these methods actually obey the law of radioactive decay over time. And so we can define a general age equation, which is the same for all of these systems. So this is the equation, which is basically takes into account the decay rate. Then we have a logarithmic function as the decay becomes slower over time. And within here, we have like a daughter concentration D over a parent concentration P, and some constant which depends on the different units of those values. And as you know, we can also simplify this a little bit, linearize this equation, and then we get like basically C over lambda, which are two constants times daughter over parent concentration. So usually those daughter concentrations are something like helium or a degree of damage or a number of spontaneous fission tracks, and the parent concentration is represented either by some isotope concentration or a number of induced fission tracks. And for example, EU is also something like this parent concentration, as it is just the recalculated uranium and thorium parent concentration. So one very interesting observation here is that actually both H and EU are within this age equation. So on the left, we see T is the H, and on the right, we see here in the denominator is the P, which is uranium and thorium, which is basically the same as the effective uranium. And this brings us to the next question: how should actually the relationship between the daughters and the parents look like? And if we're speaking about an idealized case where all our grains within one sample have the same age, we can plot the daughter concentration against the parent concentration, and we would get like a perfectly proportional line. So a linear array through the origin with all points lying there. Why does it have to go through the origin? Of course, if we don't have any parent, we won't get any daughter. And of course, in this case, also all of the data points share the same slope, and the slope here is basically the ratio of daughters to parents, and therefore a measure of the age. So in this case, we can speak about a true isochron as along this line, all of these points have the same slope to the origin and therefore share the same age. We can also summarize these properties of this idealized daughter-parent relationship in the statistical properties, which would be a perfect correlation between daughters and parents, and the same relative variation. So the variation coefficients, which is just standard deviation divided by the mean, should also be the same. So now there's the question, how does the correlation now arise? As I told you, actually in this age equation, we already have both the age and the parent concentration, and we can just simplify it a little bit and say actually the effective uranium is something like the parent concentration, and we can use it as a parent concentration. And then, well, we already that we have both of them in one equation, so some relationship must be there between the age and the EU. And this brings us into the field of spurious ratio correlation, which is actually a very well-known phenomenon in statistics, so dating back to more than 100 years that people have already thought about it. And there is actually a formula by Carl Pearson which relates a ratio or a number that is the same as a ratio to its own denominator. Why is that interesting? Well, as we can see, the age in our case is nothing else but a constant value, in parentheses here, times a ratio. And the EU is just the denominator of that ratio. So we could say the dp ratio is basically the age, and the denominator of this dp ratio is EU. And so we can actually, from this formula, calculate the expected correlation coefficient between d over p, the age, and p, which is EU, just from the correlation between daughter and parent and the variation coefficients. If we now go back one slide to this idealized daughter-parent plot, here I said in the ideal case, we have a perfect correlation and VD and VP are the same. And actually, if we would plug in those values here, we would get a value for the idealized case, which is 0, with no correlation at all between H and EU. But then, if we start deviating from this idealized relationship, the result of this equation will not be 0 anymore. And like once we start deviating from this relationship, we get some kind of age-eU association just because our age equation includes both of them. So how does this work? I got a nice sketch here where we can actually look at it. So on the left, we always have plotted the daughter concentration against the parent concentration, or let's say daughter against EU. And on the right, we have the thermochronometric age against the parent again, or against EU. So the first row, we already know this is like the idealized case where we have a proportional undisturbed system, and there all the plots, well, they lie on an isochron, so they all have the same age. Then we have a second case that we look at where we have actually a radiation damage dependent retention of daughters, where we start off with something that may be like an isochron, but then our daughter concentration saturates with higher effective uranium just because these grains here on the right, or these data, are not as retentive of helium as these on the left are. And what we get, as expected, is such a negative curve for the age-eU. But then there are actually two other kinds of deviations from this proportional case, which can also lead us to those age-EU associations. So one could be just a linear trend, but this one does not go through the origin, but it is slightly offset. And what this would give us would be actually a negative age-EU correlation, which looks pretty similar to the one that we have in the radiation damage dependent case. Then there's a second case where we do not have any systematic trend in our data. So we have some chaotic scattering between daughters and parents. And interestingly enough, we also get a negative age-EU association, which also looks pretty much the same as the one from the radiation damage dependent case. So the bottom line of this plot is actually that, well, in the ideal case where everything is proportional and undisturbed and very, very straightforward, we don't have any problem with the age-EU plot. But if we deviate from it, we can have very, very different daughter-parent relationships, which all lead to more or less the same pattern in the age versus EU plot, or which lead to the same age-EU association. So if we only see the age versus EU plot, we cannot distinguish very well which of the three scenarios we actually have. I just want to show some examples here. So this was the Raman example that I showed on my first slide. So here the right plot is the one that I already showed. We have a negative association between age and EU. But if we look at the left plot, which is like a daughter-parent plot, a damage against EU plot, we can see that actually in here we have a linear trend. So again, this trend should be nonlinear if we had radiation damage-dependent retention. But actually what we see here is a very linear trend with the systematic offset. So now, to explain this age-EU trend, we cannot resort to radiation damage, but we have to explain somehow how this systematic offset comes about. In case of Raman, this could be, for example, some strain within the grain, which is making the Raman bands broader, or maybe some asymmetry in the spectra that's also not detected and that's broadening the Raman bands. It's speculation, but of course, we want to explain why our data look like that. The second case that I have here is a helium case. And again, on the right side, we see a scattered but very strong negative age-EU correlation, which looks like very systematic. But if we look on the left on a plot of daughter against parent or helium against effective uranium, we see that it's completely scattered, like that. The relationship that should be there, that we would expect of, like, well, the more helium we get, the more effective uranium we have, is not the case here. So actually these data are completely scattered, and it is really hard to investigate here what effect is actually leading to the scatter. In this case, I would think it could be maybe very high analytical error, although I think it's pretty unlikely. It could also be like really, really chaotic loss of helium from those zircons under geological conditions, which just leaves us with a very, very chaotic data pattern that is extremely difficult to interpret. But also in this case, I mean, in these scattered data, we cannot exclude that there is radiation damage dependency of the helium retention. But also we cannot be sure if this is the case because there is no systematic dependence of helium on the effective uranium. Okay, I've already mentioned it a bit. To talk again about what causes this random scatter and those systematic offsets. So first of all, we can always have like some analytical errors or analytical offsets, like a systematic or a random error that is maybe not well defined. Of course, for the scatter, we can also have like problems with the matching of parent and daughter measurements. We can have zoning. We can have For example, in helium dating, we can have some problems with alpha ejection correction, which may be strongly inaccurate or vary a lot between different grains. And for the systematic offsets, we may have in helium dating something like parentless helium, so helium that does not come from the mineral itself, but that was implanted, maybe from an inclusion or maybe from outside the grain. We can also have like actinide-rich neighboring phases that may have still been attached to the grain during the analysis. In Raman dating, we also may have problems with strain and substitutions. So as I told you yesterday, substitutions, chemical ones, probably do not affect the Raman spectrum very much or as much, but I think strain can actually be a problem in this case. And of course, in fission track dating, we can also have problems with track counting biases, especially if we have grains full of defects or so, and we count much more than we actually have tracks. And of course, what we also should not forget, radiation damage can also affect scatter and offset. So maybe there, even in those scattered data sets, there can be an effect of radiation damage, but it may not be systematic, but very, very chaotic how it affects the retention of the daughters. Okay, this leads me to one of my last slides. So what can we actually do about it? Because now that we know about spurious effects, we obviously want to avoid interpreting them wrongly. So what I suggest would be, in any case, for every data set, plot the daughter versus parent. So be it an alpha-corrected helium concentration against EU or spontaneous fission track counts against induced fission track counts, and so on, to just see how their relationship is. Because if we have this case that we have very scattered data with no or an inverse relationship, we really should ask ourselves, what does this mean? Or why do we see this? And why is there no relationship between daughters and parents, even though the parents create the daughters? Or of course, if we have a nonlinear relationship, we can probably say that radiation damage and differential retention due to radiation damage plays a role. If we have a very simple case of a positive linear relationship, well, then we can even fit a regression line and maybe calculate an isochron age from its slope. And what we can also do, not only inspect the slope of such a linear regression line, but also look at the intercept. Because if the intercept differs strongly from zero, then we are in the area of a systematic offset that we would like to explain somehow, so why our data offset. Or if the intercept is actually near zero, then we have basically the ideal case, and then we can calculate a mean age without a problem. Of course, if we have a positive or negative offset, the mean age will be biased by that offset. And so plotting daughters against parents, then if we have a linear relationship, fit a regression line, look at the intercept, and then we can decide if we want to calculate a sample age from the sample. If we want to do it, do we do it with an isochron in the case of a systematic offset, or can we use a pooled age or a mean age in the case that our intercept is near zero? So to give you some further resources on the topic of spurious correlation, I want to recommend especially 3 works. So one, the oldest one, is a paper by Carl Pearson, which is the first source that I found on this topic, and what gives basically the mathematical derivation of the formula I showed to calculate spurious correlation between ratios. Then there is a second resource that I can highly recommend, which is a book by Felix Chase on ratio correlation. It's meant as a textbook for students and shows basically this problem of ratio correlations, also using examples from geochemistry, from petrology, and other parts of geology. And then there's, of course, the paper that we wrote, which is more specific on thermochronological data, which was published a few weeks ago in Earth and Planetary Science Letters. So to conclude this talk, we see those age-eU associations in very different thermochronometers. And what we have to distinguish is like a genuine radiation damage dependent age-eU correlation or spurious ratio correlation that arises from scatter and systematic offset. So the existence of the spurious correlation is problematic because of this effect, we cannot make a straightforward inference of radiation damage dependent retention from the age-eU correlation. So therefore, the data analysis and the interpretation must always be a case-by-case decision using the daughter-parent relationship as an interpretation tool. And if we can, of course, we should also gather additional data, such as, for example, fission track lengths, or in case of Raman, this annealing detection ratio, to make sure that we don't get trapped in an interpretation that we cannot support with our data. Okay, that's it. And yeah, thanks a lot for having me here.